pleasure to present my friend and collaborator because apparently it's not the talk today, but to have a paper about COVID simulations in the pandemic time. That is a nice adventure. But Wladimir Lyra is associate professor at the New Mexico State University, and he's coming from a PhD in Sweden with Novi. That is a great name in the atmospheres and physics, atomic physics, by the way, yeah. And Wladimir was also in many postdocs in the NASA, GPL lab, in Caltech, and the Museum of Natural Astronomy, New York. But a little inside information about Wladimir, that he coming from a master, right, in Rio de Janeiro.
Well, so bachelor's, yeah.
Bachelor's, yeah. 2003, right?
2003.
With Gustavo Porto Melo. And I just write this morning to Gustavo, and Gustavo told me that Wladimir was probably the best student in 20 years of this lab.
Let me hide here.
So we expect a lot from Wladimir today, right? So Wladimir, welcome to this meeting. Go ahead.
Thank you very much. Thank you for the invitation. It's a pleasure to be here. And as José said, I am from Rio. It's a pity that I never spent much time here in São Paulo. So it's a pleasure to be here. I was here the last time 10 years ago. I was just mentioning to Silvio that throughout my whole career, I never even been to IAG, which is like just here. So it's sorry. This is a quick bio here. So indeed, after the bachelor's in Rio, I went abroad. I did research assistantships in Germany, Chile, Lisbon, and Baltimore. And after that, after 1 year doing these research internships, I went to the PhD, went to Sweden, finished my PhD in 2009, and after that, I went to postdocs in the US. First from here to Europe, and then from Europe to the US. First, I was in New York City at the American Museum of Natural History for the first postdoc, and then I got a Hubble fellowship, which I brought to JPL Caltech. And after that, I landed faculty jobs. First, I went to Cal State, also in the LA area, and after 4 years there, I moved to the position that I am now at New Mexico State, and got tenure there in 2022, so it's been only a few years. So that was a quick bio. And the stamps that I have been collecting through these times. Anyhow, this is a course about the formation of planets. So through this week, let's understand from first principles how you form planets, how we can form planets in the universe. And to understand also why, in first place, the universe should even have planets, right? Why is it that the physics of the universe, the physics and the chemistry allows for the formation of these objects? So this is an outline of what we're going to be studying during the week. Monday, so there are 4 lessons, right? The first one is now, Wednesday, Thursday, and Friday. Today we're going to be talking about setting the stage, right? I'm going to talk about the collapse of clouds, how the disk forms from this cloud collapse, and what is the structure that we expect from these disks. The learning objective now is to understand what is the state, what is that stage, what sets the initial condition for planets to form. And throughout the week then, the next lectures are going to talk about how to form the first building blocks. We call this the planetesimals, right? So the planetesimal formation, and what are our modern ideas about how that step happens. This go by the opaque name of streaming instability, but also there are other ideas such as vortex trapping. And from that, basically, you have to, what we will understand is how the dust that is initially in the form of micron-sized grains around stars will will coagulate up to big sizes so that we can form planetesimals. Thursday, then after these big pebbles are formed and the first planetesimals are formed, how they scoop up these rocks to form rocky planets. And that is the germ of the core accretion theory, right, of how planets form. And lastly, then on Friday, we're going to talk about the formation of giant planets. There are two competing theories, the core accretion and direct gravitational instability. So that's what we're going to cover during the week. Please, at any time, if you have any question, raise your hand. Please feel free to interrupt me and ask questions at any time. One thing that I like to say to the students in my class is that there are no stupid questions. There are only stupid answers, right? I may give stupid answers to your questions, but in no way there is such thing as a question being dumb. Right. So the reading material was advertised to you by email. This is what we're going to base these lectures. There is this very nice book by Phil Armitage, The Astrophysics of Planet Formation. There is a review that I published back in 2019. Also, there are some ideas that I'm going to be discussing in this series of lectures that are there. But by and large, I urge you, if you are interested in this field, to look for the chapters of the series of books, The Protostars and Planets. These are some of the books that I have in my office, of this series, Protostars and Planets 5, 6, and 7. Protostars and Planets is a giant conference that happens about every 10 years. It serves as a snapshot of the field, right? So these books are valuable, not only for us to see what our current understanding is, but also the history of the field. So the latest one was Protostars and Planets 7. We just had the conference in Japan back in April 2023. So the chapters are fresh, right? So I'm going to be using ideas from the chapter 13, which is a chapter I'm on there. It's hydro, magnetohydro, and dust gas dynamics in protoplanetary disks. And for the hands-on session, we're going to be downloading the Pencil code, which is a hydrodynamical software to simulate these hydrodynamical and dust-gas interactions in protoplanetary disks. What you're seeing here is an MHD, magnetohydrodynamical calculation from myself, showing some of the dynamics that is happening in these disks that we're going to be looking at. Now, planet formation is an active field, right? It is something that is happening as we speak right now. Every single day there are new papers on the field in the archive, so it is quite difficult in a way to give a series of lectures about that because we need to cover the basics, the history of the field, and what's new. And there are new things every day. I teach a course on planet formation at my university since 2020, and every year that I teach it, it is different because every year there are new things, right? So these are just some of the hits that you get. Like if you just Google planet formation, and you see new things from 2 days ago, things from like 1 day ago, from a few weeks ago. It is a live field, right? It's amazing that we even have a book on the field because things change quite fast. In fact, this is the second edition. It was published in 2020. The first edition was published in 2009, and if you compare the edition one with the two, it's quite different, right? So what are the ideas that go into planet formation? What are the constraints here? We have two major constraints from, of course, the solar system and exoplanets, right? I would add another one which is very new too and fresh, which is the constraints from protoplanetary disks. And of course, the other one is the theory, right? So from solar system, what we have is very detailed observations, very detailed constraints. However, it's only from one system, right? We can actually, I mean, we can go there, we can land on the planets, and we can learn a lot from them. They are in our neighborhood, right? Our garden. So there is a lot that we can learn, but it's only one system. And then complementary, there are exoplanets, which is the very opposite. Then on exoplanets, we don't get much information from each one of them, but we have comprehensive statistics on what little information we can get, right? And theory, because of course, given the initial conditions and putting pen to paper and computer models, we can go a long way, right? If we know what the equations are. So let's start then from the constraints that we get from the solar system. Basically, any planet formation model around the sun has to explain these three properties here. First one is that all the planets are orbiting the sun in a prograde direction. Right? We don't have planets that are orbiting counterclockwise and others clockwise. They all orbit the sun in the same direction. Second, all the planes have orbital planes that are more or less in the same plane. Right? The planet that is mostly inclined is Mercury, which is inclined by 6 degrees. That's not much. What you see from this is that space, even though it is three-dimensional, the solar system is flat like a pancake, right? So these two things, the solar system is flat, and all the orbits are in the same direction, right? The third point is that there is a dichotomy between the inner planets and the outer ones. The inner planets are small, they're rocky, they're dense, and the outer planets, they are gas, icy giants, they are large planets. So there is this dichotomy between rocky and non-rocky planets. The first two, right, that the fact that we have the solar system all orbiting in the same plane, and all the planets orbiting in a single direction is a dead giveaway of the initial condition. The easiest way to obtain this configuration is to assume that the planets formed in a disk that orbited the young sun, right? And the fact that this guy here is a gas planet shows that this disk must have been a disk of gas, right? And the Earth is a rocky planet, so therefore you have dust. So that was the conclusion already from the 18th century. In the 1700s, astronomers already understood that the planets have to form in a disk of gas and dust, right? That was the conclusion in the 1790s. They didn't go much forward because, well, if it is a disk of gas, then you needed to explain it through hydrodynamics, and they didn't know hydrodynamics yet, right? Dynamics is the crown jewel, right, of the 18th century. Hydrodynamics had to wait the 19th. Not only that, then we also have chemistry. Now, just from this single idea, we can already understand some of the properties of the planets. Remember the third point, right? The dichotomy between the inner planets and the outer ones. To understand that, let's look at the chemistry, right? So what is the chemical composition? You start from this disk that was orbiting the young sun, so it had the same chemical composition as the sun. So this is a diagram that my friends who study stars and the sun tell me that's the chemical composition of the sun. And you can see here, what are the most abundant elements in order? You have hydrogen, right, helium. Pretty much everything, almost everything in the US is hydrogen and helium, right? Almost everything is is hydrogen, almost everything else is helium, and everything else here is trace, right? See, this is a logarithmic scale. So the trace quantities are what? Oxygen, carbon, neon, iron, right? Nitrogen. So if you are in the temperatures of the sun, all of that is just atoms, right, going around there. But in the colder temperatures of a protoplanetary disk, you start to form molecules, and this thing starts to condense. So you're going to partition some of this into solid, and these solids can be either ices or rocks. and the rest is going to stay in the gas phase. That depends on the temperature. But let's look at it here. What is the chemistry that we can expect from it? You have here helium and hydrogen, right? They are in the gas phase, and I'm coloring red here what is in the volatile phase. Volatile means that they are going to be either on the gas phase or on the solid phase, right, depending on where you are in the disk. There are regions of the disk where they are in the gas phase, and regions of the disk that they are in the solid phase. And then you have the refractory that by and large are going to be on the solid phase only. These are iron and silicon and nickel. And from this then, you can already expect what are the molecules that are going to form. So as I said, right, you have here 71% hydrogen, 27% helium, and these traces here. So let's put these traces in a sea of these hydrogen and helium things here. So I did here one by one to put, 100 hydrogens, and then one of, and the proportions that you expect of the other elements. And from this, you can see here, if you are a helium in the disk, you're not going to join any other because helium is a noble gas, right? So it's going to stay alone. It doesn't like to hang out with other things. Oxygen, though, most likely is going to bind to hydrogen and going to form water. The carbon here is, again, is going to bind with hydrogen, is going to form methane. Neon is also a noble gas, it's just going to hang out by itself. Nitrogen here is going to combine with hydrogen, is going to form ammonia. There is a mismatch between the amount of carbon and the amount of oxygen, so the leftover oxygen is going to combine with carbon, and it's going to make CO. But by and large, these are the molecules that you expect. So the chemistry of this disk is going to be this. Where you're going to have hydrogen, helium, right? Hydrogen is going to be mostly in the molecular form. These are in the gas phase. And then you have oxygen, carbon, and nitrogen combining with hydrogen to form ices, right? Things that are either in the gas phase, if it's too hot, or in the solid phase, if it's cold. And iron and silicon are going to form rocks, right? These are going to be the metals and the silicates. So in the end, this is what you end up with. Hydrogen 71%, helium 27%, and the trace amounts, water, ammonia, methane, these are the ices, and rocks. This is 2% of the disk. So what do you have then in the end? You have gas, you have ices, and you have rocks. So you already know how to form planets, right? In the sense that the base ingredients are there, right? You're going to form then planets that are dominant in either one of these three. Dominant in rocks, these are Earth-like planets. Dominant in ice, these are Uranus and Neptune. Dominant in gas, these are Jupiter and Saturn. Right? It's all about combining rocks, ice, and gases in different amounts. So does that make sense? When we look at the composition of the planets versus the composition of the sun, we see this trend here. So what you're looking at is the composition of meteorites, right? These are chondritic meteorites. That just means that they're very pristine, right? These are among the most pristine objects in the solar system. And here is the abundance in the solar photosphere. And you see most atoms are following, most elements are pretty much following this one-to-one line here. The other elements are very well explained by what we know about the physics of the sun, right? And stars. Lithium is high in meteorites, but is destroyed in the sun because it can get onto the bottom of the convective zone and the burning. And these are elements that are abundant in the sun, but they are lost in meteorites because they're too volatile. They're always in the gas phase, right? And here you have the ices, right? The ices, you see that they are also above this line, but not by much. So there is some separation going on here. What we expect is that if these elements, C and O, right, they are sometimes in the volatile phase and sometimes in the rocky phase, in the solid phase, there must be somewhere in the disk where you do a transition, where you have a transition in temperature, and these objects pass from being in the gas phase to being in the solid phase. This is the snow line, right? The snow line of water. In the inner part of the disk, right, there is no ice, so that's just rocks. But then you cross a region here, a radius, where the temperatures are low enough the ice forms, and these species will condense ice, water, vapor will turn it into ice, and then you have ice all over beyond this region. Then with this, then you can more or less roughly explain the dichotomy. All right, that you have that the accretion of planets in the inner part was free of ice, so you only had rocks. Right, the abundance of these rocks is low because you only have iron and silicates, whereas in the outer part you have oxygen and carbon that are much more dominant in abundance. There is more raw material there to form bigger things. So you form icy cores. All right, ice comes to aid beyond the snow line. You end up growing bigger cores, right? Bigger cores that are made of both ice and rock, whereas in the inner part you only have rocky ones. And then something happened in the outer disk that these two here remained icy, whereas these two here got so big that they started creating gas from the nebula. So that was the idea back 30 years ago, right? That could more or less explain in qualitative ways the main characteristics of the planets around the sun. Of course, the surprise came with the exoplanets. We ended up finding Jupiter-sized planets very close to the star, right? And other sort of exotic planets that the exoplanet revolution confirmed some of our ideas about how planets form, but also challenge other ones. And that's something that we're going to go through too. But let's see here in a little bit more detail how this play out. First, one of the first attempts to try to explain the distribution of material in the disk around the sun is called the minimal mass solar nebula. The idea here is to find out what is the minimal mass that this disk around the sun must have had to form the planets and almost nothing else. So how does this go here? You take the mass of a planet and spread it through its orbit. So that's what's being shown here. This is the orbit of Jupiter, right? The orbit of Mars and the orbit of Saturn. So you take the mass that is in Jupiter now and spread through its orbit halfway to the distance to the neighboring planets, right? So the boundary here is half of the way to the orbit of Mars, and the other boundary here halfway to the orbit of Saturn. And as you can see, what you're doing is that you're converting this mass into a column density, right? Into a surface density. And in this way, you can map what the original column density was everywhere in the disk, right? The other thing is that we don't know what the original composition was, but we can make the assumption that it was similar to the composition of the sun. So you take the composition of the planets now, and then you add hydrogen and helium until you match the composition of the sun, right? Because if you play this game with the Earth, you're going to have only dust, right? There is going to be no gas. So you needed to add gas to match the composition of the sun. Doing that for every planet, then you end up with this plot. So what you see here is the distance to the sun, right, in astronomical units, and here the column density that you get by doing this exercise. So these would be Venus, the Earth, right, Mars here, Jupiter, Saturn, Uranus, and Neptune. See that you have something that looks very continuous, right? And then you have some ideas of what may be going wrong here. Maybe Mars got lost too much mass. So that was actually a big problem in the field why Mars is so small. This is the asteroid belt clearly lost some mass, right? The original asteroid belt should have been orders of magnitude more massive to fit here in this plot. Something off here with Mercury too. But by and large, you can trace a line here, right? A power law, right? So this gives us a power law of minus 3/2 for the column density of the disk that orbited the young sun. This is from 1977, and this is a kind of more modern version of the same plot, but the idea is pretty much the same, right? You have here the line of the rocky planet. You augment this mass here by 600 by adding hydrogen and helium until you match the composition of the sun. For the giant planets, you only need to increase the mass by about 8 to reach solar composition. For the ice giants here, you add about 100, and then you end up with this line here that seems to be a power law of index minus 3/2, right? Now, I guess that I'm going to be the first one to use the board during this, but let's do a quick math here to see what is the mass that you expect, right, if this is the, the composition. Oops, sorry. Right. So we have this mass then, right? So the column density, and I'm going to call it sigma, it's about 3,000 right, grams per cubic centimeter. And then falling with the power law of minus 3/2. Take this and then integrate it up to about 30 AU, which is the orbit of Neptune. What do you get? So integrate this to 30 AU. What is it that you're going to find? You got 2 pi, right, for the azimuthal integration that we assume to be axisymmetric, and then you need to give a minimum limit. The minimum limit is not going to matter because of the power law, as we're going to see. And then give this column density and also give the Jacobian in cylindrical coordinates. There we go. Integrate this, and then you find what? 2 pi. Give the sigma naught here. Let's call this quantity here sigma naught. Sorry. Right. If you do this integral, find that the mass is going to be then 4 pi sigma naught AU to the power of 3/2. And then integrate is going to give you the square root of R1 minus R naught. And that's why R naught doesn't matter, because if you integrate to 30 AU, this number is going to be much bigger than this, so you can ignore this. 0 in comparison. So 4 pi 30 AU times 1/2, square root of 30, you end up with about 3 times 31 grams if you substitute the numbers. So 3 times 31 grams. That means that the mass of the disk is roughly 1% of the mass of the sun. All right, the mass of the sun is 2 times 10 to the 33 grams. All right. So that is the mass that the disks should have. And by and large, this is the distribution of masses that is seen. right? When we look at protoplanetary disks around the other stars, this is a plot here showing the mass of the star and the mass of the disk. And this line here is the 1% line. So there is some considerable spread, but it's amazing that this very simple model already gives you the right order of magnitude. And look what went into this calculation here. Some very strong assumptions to plot this line here. First, you are assuming that planet formation is 100% efficient, that all of the dust went to form the planets, right? That is absolutely preposterous, but seems to be giving you the right order of magnitude, at least, you know, even if there is some spread there. And second, that the planets did not migrate. You're expecting that the planets formed where they are, right, and then did not move, which, from what we know of physics, doesn't need to be the case. We expected that planets, once they form, they're going to exchange angular momentum with the gas and then change their orbits. That's actually how we explain the existence of hot Jupiters. But the fact that we are getting this right seems that to say that there is something right about this idea. And at least it can be useful for as a starting point. Right. So we see here that we can trace the planets, indeed, to a disk that formed around the sun. How does that idea apply then to other stars? For that, we need to go back one step and examine star formation. What happens, right, when stars form? What you're going to see here is a simulation of a cloud. This is a giant cloud, about 50 times the mass of the sun, and then collapsing under its own weight and turbulence. What you see here is that the fragmentation of this cloud is not uniform, right? It's turbulent all over the place. And it is not that you form stars through direct gravitational collapse, right? Due to the turbulence, what you have is some regions, some pockets of high density, and some pockets of a low density. The brighter yellow here are the high density regions of this cloud. And it's in these pockets, these high density pockets, that stars are going to form. So as I said, right, you have this big cloud here, 50 solar masses. Following their collapse, you have some high-density regions where you go above the Jeans mass, and then stars start to form. This whole calculation, by the way, takes about 300,000 years, right? Like not of wall time, but of physical time. You see here that some of the stars are forming here, forming with gas around them. Right. Pretty much we expect every star to be formed with gas around them. The reason why not all of them in this calculation have them is just the resolution of the calculation. But the more massive stars here have the resolution for you to see that there's some gas forming around as they're born. You can see here, right, this one star, there's plenty of gas around here, that one here too, this one, right? And so zooming out then, you see the cluster that forms from this. And this looks very similar to some of the clusters, right, that we know. This is the Orion Nebula cluster, the Pleiades, and the Hyades. When you zoom in into some of these clusters, you actually see some objects that are very interesting too. These are called Bok globules. These are dark regions in cluster, dark clouds. They're so dark because they're very dense and have a lot of dust in them. The only reason why you see them against this background is because you have the bright background from the nebula. All right. This one here, Barnard 68, looks like a hole in the sky, right? You have this very dark, dusty gas, right? It looks like a keyhole in the sky. This is a cloud that, if you measure the mass here, which was done for this mapping, Here is in visible wavelengths, and here is in infrared. So you can measure how much extinction you have at each point of the cloud, and with that map the mass, right? So this is the extinction versus arcsecond from the center of the cloud. This then allowed them to measure the mass, and it turns out that this is a 2 solar mass cloud. So this is going to form 1 star only, right? This is a globule from which a star and hopefully planet at some point then will form too. So the mass here you can see, well, I mean, you don't see the mass from this, but believe me when I say that this converts to about 2 solar masses, but you see the size, right? The size here is about 10,000 AU. So it's not yet the scales of protoplanetary disks, right? The solar system itself goes about like 50 AU, right? The cliff in the Kuiper belt, but we don't expect the disk actually to expand much beyond that, maybe like 100 AU or so. Other information that we can get from these globules is their rotation. You can measure the radial velocity in different parts of the cloud. And this is what is being shown here for 3 different of these objects. So this is red shifted, right, and this blue shifted. It means that this side here is moving away from you, right, and this side is moving towards you, right. So this is moving towards you, and this side moving away from you. So this is rotating in space. So that gives us a measurement of the rotation of these clouds. Same thing here, blue shifted towards you, red shifted away from you, blue shifted, red shifted. And so what is it that we can measure here? We can measure the speeds, right, and the sizes. So that gives us a measurement of the kinetic rotational energy of these things. Right, so let me do some little math again here. You see that this cloud cores, they have scales of what? 0.1 parsec, right? This cores, so their scale there, what was that? 5,000 AU, 10,000 AU. So a parsec is of the order of 100,000 AU. So these cloud cores have scale of about 0.1 parsec, and their densities from those mapping, they give you about a number density of 10 to the 5 particles, right, per cubic centimeter, right? So in 1 cubic centimeter of space, you have about only 10 to the 5 particles. We can define a quantity here, which let's call it beta, and that's going to be the rotational kinetic energy divided by the gravitational energy. Right. So the rotational kinetic energy, you remember that from physics 1. It's half of the inertia moment times the square of the angular frequency, right? And then the gravitational energy is 3/5 of gm squared over the radius. Well, these quantities we know. So if you need a refresher about inertia moment, remember it's this quantity here that you get by combining the arm, right, versus the speed. So mr squared. Sorry, not speed. The arm, right, and the rotation. So you get here mr squared from that dimensional analysis, And homogeneous spheres have the coefficient in front of it being 0.4, right? This plot here is showing the deviation of homogeneity for objects in the solar system. You see the moon there is almost a perfectly homogeneous sphere, and then this is a measurement of how concentrated these objects become, right? As you deviate more and more from homogeneity, the moment of inertia falls more. So as you see, Saturn is very concentrated, shows that there is a very dense core, right, in the middle, and then the outer parts are fluffy. But that is a side thing. What I want from this is to write the moment of inertia as little p here times mr squared, and p for a homogeneous for uniform density is 3.5. So what we can write here then is this quantity beta to be then half of this p here over 3/5. Then omega square r cubed over gm. Now if we have a constant density, then we can substitute this mass here by the density. Write the density as 3 times the mass over 4 pi r cubed. So this beta here, you can do the algebra yourself, becomes omega squared 4 pi g over the density. And these are quantities that we can measure. Omega is the angular speed. You are measuring in that observation the radius, and you're measuring the linear velocity. You divide one by the other, have the angular velocity. And the density, yeah, it's also measured from the observations from the column density. That's this number here. What you find then is that this number gives you 0.02. What does 0.02 mean? So this quantity, this shows here the distribution of this quantity beta measured for several of these objects. So this is a histogram, right, of this quantity. You see there is an average of about 0.02, indeed. So this quantity is the rotational kinetic energy divided by the gravitational energy. That means that rotation almost doesn't matter, right? It's a very small amount of rotational kinetic energy in these objects compared to the gravitational energy. So these clouds are not rotationally supported. So you would be tempted to completely ignore the rotation. However, when you compute even with this very small amount of kinetic energy in the rotation, if you measure the angular momentum, then you find something very fishy. So let's see here what the angular momentum of the core is. So for this quantity beta, right, we can write, let's see here. First, the angular momentum should be mr cross v. So write that in terms of angular quantities, that's m omega r squared, right? And we can write this then in terms of beta. We can write omega, if you just rearrange this, omega is 3 gm beta r cubed, and then you take the square root. So you can write the angular momentum of this being mr squared, and then omega 3 gm over r cubed. Take the square root, and beta to the square root. All right. There are some steps of algebra here that I'm not going to repeat, but if you plug the numbers of this course, you find then that the angular momentum should be about 2 times 10 to the 54 grams centimeter cubed per second. and then some scalings. The mass with beta, normalize beta here by 0.2. And the typical radius, 0.0 parsec. Right. What is important here is this number, 10 to the 54. That is the typical angular momentum of this cloud course. How does it compare to the angular momentum of the solar system? There you go. This is the distribution of angular momentum in the solar system. There is a dichotomy here, which is actually a very interesting problem. Why is it that the angular momentum is not where the mass is? The mass is in the sun, but the angular momentum is in the planets. Most of the angular momentum of the solar system is in the orbital angular momentum of Jupiter. All right? And even that pales in comparison to how much angular momentum the cloud had. The cloud has about 4 orders of magnitude more angular momentum than the solar system. So how do you get a giant cloud compacted to form a planetary system and not conserve the angular momentum? Right. Houston will have a problem, right? So this is the angular momentum problem of forming planets to start with. Well, somehow the angular momentum was lost from the cloud core as it formed the solar system. So how did that go, right? Did it go into a binary? Did it go into somewhere else? If all of this angular momentum has to be lost, right? Anybody have any clue at what happened? Yes? Sorry? Solar winds. I can see why you'd think that. But for the system to lose angular momentum through solar wind, the angular momentum first must get to the sun, which doesn't seem to be the case. Right? The sun has actually very low angular momentum. In fact, what is going on is that this angular momentum never reaches the solar system, right? At least not by that much. There is something going on there that when the sun was formed, the mass went to the center because it lost angular momentum. You transport the mass inwards, and the angular momentum is transported outwards. You separate the mass from the angular momentum, mediated by a disk. These are called accretion disks. Yes? Through magnetic fields. That is another, yes, exactly. That is a very good point. Indeed, our more modern ideas of how this angular momentum is transported is indeed mediated by magnetocentrifugal winds. But the first idea that the field had was actually through turbulence, because turbulence can behave like viscosity, and viscosity transports angular momentum. So, but we are putting the cart ahead of the horses here. We're going to talk about that in the next lectures. What I want to show here is that you can accommodate this angular momentum if you form a compact disk. So when this globule collapses, it doesn't collapse immediately to form a star. There is no way that you can do that with that much angular momentum. You first must form a disk. And this disk is containing the angular momentum that the cloud had. And then there is another question: how do you transport angular momentum from the disk to form the star in the center, which is an object of low angular momentum compared to the cloud? But at first, we can estimate exactly how big these disks would need to be to accommodate the angular momentum of the cloud. Now, let's see this. What if all of the angular momentum gets stored in a disk? Let's ask this question. If all the angular momentum of this cloud is stored in a disk, how big will the disk be? Right? So you have this angular momentum here. Try to store that into a disk. How far will this disk go? So for that, let's think about the specific angular momentum. which is the angular momentum of the score divided by its mass. This is a measurement of how much angular momentum a single gram of this cloud mass has, right? So J of the core over the mass of the core. J is the angular momentum. So you have then 2 times 10 to the 54. Let's not forget the units. Divided by the mass of the core. In this case here was 2 solar masses. So 4 times 10 to the 33 grams. You find then that the specific angular momentum is about 5 times 10 to the 20 centimeters square per second. And for the disk, what is the specific angular momentum? For the disk, you're going to have that this is omega r squared. Omega is the frequency that the gas is rotating, right? And r here, the radius where you want to go. So omega, given by Kepler's law, right, the Keplerian frequency, is square root of gm over r cubed. Then r squared here. Cut this becomes the square root. So square root of gmr, right? Equate these two now. Equate these two and solve for the radius. You find what is the radius that gives you the specific angular momentum of 5 times 10 to the 20 centimeters squared per second? Solve this. You find a radius of about 1.8 times 10 to the 15 centimeters. 1 AU is 1.5 times 10 to the 13. So this is about 100 AU. QED. So there is no way to form a star directly from the collapse of the cloud. You first must store all of this angular momentum in a disk, in a centrifugally supported structure. And just by this quick math here, you get the order of magnitude that this disk must be in size. It is about 100 AU, exactly the size of the solar system. So let's look at the night sky and then try to find evidence of these disks around young stars. So this is the Orion Nebula. Let's zoom in. Look for disks there. I zoom in more. You have to zoom in so much to find them. There we go. Woo. Right. So this is a protoplanetary disk against the bright background of the Orion Nebula. I'm a theoretician. Yeah. Right. Well, yeah, this is, yeah, exactly. Yeah. So let me zoom in again, so you go there, see. But this is about, indeed, about 100 AU. You see that, you see more objects here, seeing with HST against the bright background of the nebula. And this is invisible, right? Because this is done by HST. So the wavelength that you're looking at here are visible wavelengths. But of course, we have a multi-messenger. We can look at it with other, in other wavelengths. SMA is the submillimeter array. And the biggest revolution in the field in the past 10 years has been ALMA, the Atacama Large Millimeter Array. When you look at this, so this is the size of the beam here, right? This is just fascinating. So ALMA has really staged a revolution, right, in the field because of the resolution that we can get. So some people talk about the ALMA revolution. I would say that is the ALMA resolution. Right, that enable that. If you take the solar system and put it 140 parsecs away at the distance of the nearest star-forming regions, this is the resolution that you would need to resolve it, right? The whole solar system would have about 0.7 arcsecond, right? This is what you could do before ALMA, 0.3. So you put this beam there in the solar system, you smear everything out. ALMA is now able to do about 3 AU resolution at 140 parsecs, right? The resolution that has about 0.02 arcsecond and pushing, right? Every year that passes, yeah, we are pushing more and more the resolution. So this is what ALMA could do before. I'm sorry, this is what we could do before ALMA. This is HL tau seen with SMA, the sub-millimeter array. And this is ALMA on the same source, HL tau. See the level of detail. Pretty much everybody who works in the field since at least 2014, which was when this image was released, knows exactly what we were doing when we first saw this. Because like the headline was like, this is not a model, right? This is an actual observation. So the amount of detail that we get from this. And this was ALMA in 2013, 2014. This is ALMA now. This is the amount of detail that we can get from these protoplanetary disks. So remember what I said in the beginning, right? To have different lines of attack to understand planet formation, the constraints from the solar system, the constraints from exoplanets theory. We also have now the constraints from protoplanetary disks from observations of protoplanetary disks. Because it's a very different game in this field now than it was 10 years ago pre-ALMA. So it's been some very exciting 10 years. So what did we learn from this? This is one of the most recent big surveys of disks. So here is paper from 2020. And what is seen here are different star-forming regions, right? Ophiuchus, Taurus, Auriga, Lupus, Chameleon, and Upper Skull. And these are the radius of the disk. So the radius that are seen with SMA and the radius seen with ALMA, then we're able to see smaller disks too now. And they all converge at about, indeed, disk radius of about 100 AU, right? So again, fitting here this simple analytical estimate that we just did. The distribution of disk sizes, right? So this is the mass versus radius of these disks. So seems to be kind of a little all over the place, but yeah, there doesn't seem to be much of a correlation with the mass, which is kind of expected because it depends on the square root of the mass. So square root is a very slow function. But you see here distribution of disk sizes versus different classes of objects, and I'm gonna explain what classes are. But what you see here is a distribution that hints at something evolutionary, right? That you have these disks that are bigger, right? So you have here a big number of disks that are about from 0 to 200, and some that are about 100, and then you have other disks that seem to be more spread out, right? So it turns out that if you see this, if you think that this is some evolutionary sequence, these ones must be younger than these ones. Because if we expect the disk to spread out, right, the angular momentum has to be lost, so the disk must spread out. You start in this way, and then you spread out the disks from this so-called class 1 to this class 2. Right, but in the next few minutes, then let me go through what we mean by these classes. But before I do that, do you have any question? Right.
Question, comment.
As I said, feel free to.
I have one comment about this angular momentum. I mean,
Huh?
you write the angular momentum here, and you have Jupiter, right?
Yes.
If you put Jupiter inside the sun, you change that. So have you compared these values with stars, with planets that we have now? I mean, because almost all stars has some planets, but some of them has Jupiters. So if you take into account Jupiter in this solar angular momentum, what to expect? Yeah, exactly. So.
Yep, there's a very good point. It would be amazing to do this plot for the exoplanets. And then you have to think, what is it that we need to create such a plot? It doesn't seem to be much. You need to know, though, the rotation of the star, right? Yeah. So if you can do, if you can do this plot for a different number of stars and different number of planets, that would be fantastic plot, I would say. Because, yeah, the other quantities that go in here are the mass of the planets, the distance this we have. What we don't have here is the spin angular momentum of the star. Yeah.
Yeah, second thing is that the star has the internal rotation as well.
Of course.
That this takes some angular momentum
Yeah.
from the system, right?
Yeah.
So that's probably another point.
Yeah.
Second question is about the chemistry.
Mm-hmm.
Your planets in the first part of the lecture, you talk about iron in all the planets,
Yeah.
but probably you have some planets without iron. What
Yeah.
expected?
Right, indeed. Well, the iron and the silicates, you expect actually from the chemistry that there are some solids that are iron poor and some solids that are iron rich. But in the chondritic phase, when you have sorry, let me dial it back a bit. This separation between silicates and iron actually comes already from the differentiation of these objects. Right? Once you have them all mixed, most of the compounds that you're going to make with silicate are also going to have iron. It's hard to find a chondritic, which is a pristine, undifferentiated object, where iron and silicates are separate. You need to aggregate so much mass so that you have energy to melt the object so that the iron sinks to the center and the silicates go to the surface. Yeah.
Thank you.
Cool.
Another question?
Right.
Oh, okay, thank you.
Okay, cool. Well, as I said, please feel free to ask any question during the talk. I wouldn't want this to be a monologue. But okay, what did we learn so far? What are the key ideas so far? The planets forming disks of gas and dust. Gas means that's about 99% helium and hydrogen. Dust means mostly ices. Dust means ices and rocks, right? The refractory and the volatiles. A collapsing cloud has too much angular momentum and it will form a disk of about 100 AU. And these disks have about 0.01 mass ratio, meaning 1% of the mass of the star, although they have a considerable scatter. So I hinted at the different classes of young objects. And what you're going to see here is that there is an evolutionary sequence on the types of disks, right, that we expect, that we see. We call these low-mass stars T-Tauri stars, because the first object where this spectral pattern was seen was the T star of Tauri. What you're looking at is a sketch of the spectrum. Right? We have here that this is the black body of the star, right, in dashed. And T-Tauri stars, they have two conspicuous patterns. They have a UV axis, right, a little UV axis, which we understand as a sign of accretion, right? There is gas that is being accreted onto the star, it hits the surface of the star and generates a hot spot that is bright in UV. But then we also have this infrared axis here, which is hot dust. It's hot dust around the star. Now, another thing that we can measure is if you have a cluster, you can measure how many stars in that cluster have this infrared axis, right? So they did that for several different clusters and measure this infrared axis, right? How many stars in that cluster have this infrared axis? And then you can plot this plot here. Each one of these dots is a cluster, right? All the stars have the same age. And then this is the fraction of stars in the cluster that have an infrared axis. You can clearly see here an exponential decay, right? This is an e-folding time. This is an exponential with an e-folding time of about 2.5 million years. So you can expect that disks are going to dissipate in about 40 folding times, so about 10 million years. After 10 million years here, you can see that disks are pretty much gone. So that gives you two key points here. First, that's how much time you have to form planets. 10 million years is your deadline, right? The disk is going to be gone by then. At least if you want to form gas giant planets, you need a gas. So the gas is dissipating in about 10 million years. And second, if these disks are evolving in time, any static description is not the full picture, right? These disks are evolving in time. Now, a quantity that observers like to use to characterize this is called the spectral index. And I'm only mentioning spectral index because it's pretty much widespread in the literature. I prefer to work with infrared axis. But the spectral index, I'll give you the definition here. They call it alpha IR, is the derivative of the log of the flux by the log of the wavelength, right? So this is called spectral index. And as you can see, it's pretty much the same for wavelength or for frequency, which is a very useful thing if you have both optical astronomers and radio astronomers in the room, right? Because optical likes to work with wavelengths, and radio astronomers like to work with frequency. Right, so this shows here that this spectral index is correlated with the infrared flux here measuring the end band. You can plot here, I mean, you can plug here, this is supposed to be a lambda, sorry if it looks like an X. And if you substitute the black body flux here, you see, you will find that the alpha flux of a black body is 3. Right, so alpha black body is 3, actually -3 here. You can just substitute the black body flux there and find a -3, which coincides here with 0 infrared axis, right? So 0 infrared axis meets here at the -3. Higher alphas, higher spectral index means more infrared axis. So you can grosso modo define the different classes by the amount of infrared axis that they have. So class 1 would be objects that have infrared axis alpha index above 0. So this is class 1. This would be class 2, and these would be class 3 objects. So class 3 objects have almost no infrared axis. Class 1 have a lot of infrared axis, and most objects are class 2. And this is the shape of the spectrum of these T-Tauri stars. As I said, right, class 3 is almost just the black body, right? Almost no infrared axis. Class 2, you have the black body here, you have a lot of infrared axis, and class 1 even more so. This is interpreted as an evolutionary sequence. What's going on here is that at the class 1, you still have envelope, gas envelope from the cloud core that is falling, still forming the disk and forming the star. Class 2, you have the disk formed, the envelope is gone. And then class 3, the disk is gone. It's pretty much just the star, right? The infrared axis has been gone. There is no more hot dust around the star. And of course, because when they first thought about these classifications, they didn't envision that there would be an even earlier object, and so they called it class 0. Hopefully there won't be any class -1 in the future. But the class 0 is just the cloud core. And you see here how the spectrum looks like. So the black body of the star, right, the class 3, some infrared axis on class 2, more infrared axis on class 1, and almost no optical at all, or infrared even in the class 0. All of the flux is in millimeter wavelengths. So that's the picture then that we have of these objects. As I said, class 0, you have the core still collapsing in the center to form the protostar. Almost no rotation support. On the class 1, you have the envelope still falling, but the disk mostly formed. And on the class 2, then the envelope is gone and you only have the disk and the star. The star is mostly with the mass that it will have. Class 2, class 3, you're dissipating the disk. Class 3 would be what we call debris disk these days. And they added here class 4, which would be a very mature solar system with almost no dust. left, and absolutely no gas. So this is another view of how these objects will be looking like, right? From class 1, 0 to 1 to 2, and to 3. And what you see is that most of the objects seem to fall on the class 2. So this is where these disks spend most of their time, right, being. So as an evolutionary sequence, the class 0 and class 1 are very fast. Class 0 is only a few 100,000 years. Class 1 lasts for less than 1 million years. The class 2 phase is long. It's about 1 to 10 million years. And the class 3 is anything that happens after that. And if it goes from 1 to 10 million years, we expect the class 2 phase to be the main phase of planet formation. Right. Okay. One last thing, then, is that one of the reasons why ALMA is so interesting is because the wavelength of choice. If this is the typical spectrum of a class 2 disk, this is how you map the different regions of the disk to the spectral energy distribution. We have here the black body of the star, right? And then you start having the hot dust. And this is the warm dust. You have the optically thin infrared. And it's in the millimeter wavelengths that you are in the Rayleigh-Jeans tail, the optically thin tail of the distribution. So if we want to witness planet formation, infrared is not a good choice, even though infrared is the workhorse of star formation. It's optically thick for us. It stops at the surface of the disk, right? If we want to see what is happening in the mid-plane of the disk, you need to go to millimeter wavelengths, where the disk is optically thin. Or radio, where the disk is even more optically thin, but then you run into the problem that you don't have much, much flux even to start with. And then, so this is an example of a spectrum. This is the star R Monoceros, and you have several different components here. That's actually quite interesting to see what's going on. And you can disentangle where the different parts are coming from. Here's the black body from the star in green. The surface of the disk, right, you see it is this red part here. The surface is hotter because it is intercepting directly the light from the star. As I said, it is optically thin in infrared. So this region here is going to process and re-radiate. The interior is being actually illuminated from the surface. It settles then to a colder temperature. So you have a colder black body here in blue. And then you have the envelope here, which is an even colder black body. It's in yellow here. And to fit this tail here along wavelengths, you need to fit a free emission, which comes from outflows from the star. All right, let me stop here. Just want to say this last thing, right? There are new developments since from the 80s and 90s. We saw now the observations of a protoplanetary disk. There are being other things too, such as the discovery of Kuiper belt objects, which are the frozen leftovers from planet formation, discovery of extrasolar planets too, and in theory land, there's been new models, so the core accretion model, the streaming instability, and the pebble accretion model that we're going to be studying in the next lectures during the week. So thank you very much.
Excellent, thanks. Excellent lecture. So questions now, suggestions, and comments. Go there.
I think I didn't understand quite right, but the minimum mass solar nebula that you computed, the 10%, 1% of the solar mass, is the mass of the nebula in the initial phase for forming the solar system?
It's the mass that is found if you spread out the mass of the planets into a disk. So it's essentially what you expect if you start from the planets and augment their composition to the chemical composition of the sun. Right? Get the mass of the planets, add hydrogen and helium until you match the composition of the sun. That's the mass that you get. But that's the mass if planet formation is 100% efficient. Right? It's the mass to form only the planets and nothing else.
More questions? You're right. Over there.
Right, right. Yes, of course there is. Very good question, thanks. Indeed, you see here some disks. It's just like galaxies, right? There are some galaxies that are face-on and some galaxies that are edge-on. AGN disks also edge-on or face-on. And you get different information from them. There are some disks that are edge-on, like this one here. And yeah, you can see here some features that when the disk is face-on, you can, and vice versa, right? So a complementary view of these observations take into account this effect of inclination. In fact, there are colleagues of mine now working on trying to find a signature from one of these planet formation mechanisms that can only be seen if the disk is more edge-on, right? Yeah.
More questions?
So sorry, maybe you already answered this in part, but in the simulations that you showed, when do they actually start? I mean, how do you get those initial conditions, and what is the actual resolution that you get in the end? Is it an adaptive? Typically, you guys use adaptive codes, or how actually close to, point objects can you? Well, not point objects, but to the actual objects can you get?
Thank you. That is a fantastic question. Thanks a lot. We have conferences about your question. Yeah. Like, what is the initial condition we put here? As I said, it seems that these disks spend most of their time. Let me just pull here. It seems that disks spend most of their time on the class 2 phase, right? So we tend to start the simulations on the class 2 phase. However, the class 2 phase is already 1 million years in, right? There are arguments for starting at the class 2. First, yeah, because that's where most of the disks are. Second, because it's easier, because most of the mass is already gone. You don't need to take into account the self-gravity of the disks, which complicates things even more. But more and more, we are actually seeing that there is perhaps a mismatch between the amount of mass in exoplanets and the amount of masses that is measured on class 2 disks. Class 2 disks seem to be less massive than the amount of mass you see in exoplanets, right? So that is a problem, because if you form the exoplanets from class 2 disks, and class 2 disks don't have enough mass, might mean that actual planet formation starts on class 1, right? So we are seeing the first works that are starting the simulations from class 1 disks. Yeah. And the second part of your question, the resolution that we use. The resolution, of course, depends on the process that you want to see. We tend to divide them into global models, where you model the whole disk, or local models, where you only model a patch. I'm going to be showing both of them in the next lectures. But by and large, the resolution is constrained by the computational power. So the biggest model so far has used about 10,000 points in radius. But that's only radius. For that, they had to compress other directions. We're pushing the limits to computations with about 1,000 points cube, so 1,000 points in each direction, so about 1 billion grid cells per model. That's where we are at the moment in the field.
All the last questions over there.
So I'm guessing you have to form a protostar, and by doing that, you need to accrete mass, right? So what happens first? First, you lose the angular momentum, and then you accrete mass to the protostar, or is it the other way around? How does that?
It's concurrent, because what happens is by viscous stresses, you transport angular momentum outwards. By doing that, the mass has to move inwards. So the process is that all of the mass moves inwards with a 0 angular momentum, and 0 mass moves outward, carrying all of the angular momentum. That is the self-similar solution. In fact, you can show that. Probably have a slide here with that. Oh, there we go. So that's here. This is the analytical solution of a viscous spreading. You start with this very thin ring here, right? Centered at 1, and these are snapshots at different times. So this is called viscous spreading, right? As you see, the mass here is peaking. The peak is moving inwards, right? So the mass is moving inwards, but there is some mass that is moving outwards. If you go it to infinite time, you're going to see that all of the mass is moving inwards, and an infinitesimal part of the mass moves outward, carrying all of the angular momentum.
Last questions, one more. So let's think again, Wladimir. And
Thank you.
I think you have now the coffee break, right, in the hands-on session.